Hi, and welcome back to Common Core Algebra II, 4.12, the number e and the natural logarithm. Basically, there are 5 important numbers in mathematics. 4 of them are 0, 1, I, which we haven't gotten to yet, and pi. And the last one is the number e, which we're going to talk about today. So right now, just for a moment, I'm going to show you a quick video that's talking about the number e.
We've made a video about pi, the ratio of a circle's circumference to its diameter. But there's a less famous but equally fundamental number known to anyone who's taken high school algebra. It's about 2.718281828459045 and so on. And it was first defined by Jacob Bernoulli, but later Leonhard Euler called it E, and the name stuck. Bernoulli first defined E through compound interest. Now, compound interest says that you get a little bit of money in interest every period, and that money you gained helps you gain even more interest next period. In other words, your interest compounds. So if you stick $1 into a bank account with a 100% interest rate compounded annually, you'll get $2 at the end of a year. If it's compounded semi-annually, you'll end up with $2.25. Quarterly, and you'll end up with $2.44. Monthly, $2.61. Weekly, $2.69. See where we're going? If you increase the number of compounding periods a year towards infinity, then you'll get closer and closer to E dollars. In statistics, it describes the most important statistical distribution, the normal. In biology, it models populations of species through the logistic function. In physics, E describes the exponential decay of a radioactive material. So while E may not be as famous as pi, it's easily as fundamental and immensely important to its diameter. But there's a less famous, but E.
Okay, so the number e. So like pi, e is irrational. It's about 2.72, just like pi is 3.14, so it gives us an idea about what e is. And we use it for exponential modeling, among other things. But for the purpose of this course, it's basically going to be used for exponential modeling. So exercise 1, which of the graphs below shows y is equal to e to the x? Explain your choice and check it on your calculator. So if we can just make sense of this, we know that e is approximately 2.72, so y is equal to 2.72 raised to the x power. So we know here that our x-intercept is 1, our y-intercept is 1, and our base is greater than 1. So we know this has to be an increasing exponential function, which of course we know this is not. This is a quadratic function. This is definitely not an exponential function. 3 is a decreasing, so the answer is going to be 2 here. It tells you to check it on your calculator. So I'm just going to pull up the calculator for a minute. Hit my graph. And we're going to put in y equals e. Now e you find down here by the pi, down at the left. Let me just show you this for a second, right here, if you can see that. So if you hit that button, now it's not going to let me do that, so delete that. So if I hit this button, I come up with e. Why won't it let me do this? Oh, it will. Okay, delete, delete, delete. Oh, come on. And then raise it, use your up arrow to the x power. All right, you know this calculator is never too happy. So there we go. So we have an increasing exponential function with a y-intercept of 1 and an increasing function. So let me just get rid of the, oh, I can't do that. I have to do it this way. Okay, so let's drop down our calculator and bring this back, an explanation. And here, this is where you can write exactly what we just talked about, that because e is a positive number, 2.72 approximately, it's going to be an increasing exponential function with a y-intercept of 1. All right, so take a minute and write that down, and then meet me at exercise number 2. So very often E is involved in exponential modeling of both increasing and decreasing quantities. The creation of these models is beyond the scope of this course, but we can still work with them. So taking a look at exercise 2, a population of llamas on a tropical island can be modeled by the equation. Let me just pull it down so we can see it. P equals 500 times E raised to the 0.035 T, where T represents the number of years since the llamas were first introduced to the island. So A, how many llamas were initially introduced at T equals 0? Show the calculation that leads to your answer. Now I'm hoping that you're remembering the time that we actually defined what an exponential function looked like, and 500 is going to stand out, because if you remember, this is what we wrote down. Initial times 1 plus or minus the rate to the time. But if they want you to show the calculation, then we're going to say P of 0 is equal to 500 times E 0.035 to the 0 power. So we know that you're going to get 500 times E to the 0 power. Then we know any number raised to the 0 power is equal to 1. So 500 times 1 is 500. So there's our initial value. And moving on to B. Algebraically determine the number of years for the population to reach 600. So population to reach 600, pay attention to what information they're giving us, and make sure we're rounding our answer to the nearest tenth of a year. So I'm going to slide this up because we're going to need some serious room for this one. So if we start with our population to reach 600 means our P of T is 600 is equal to 500 times E raised to the 0.035 T. And I'm going to remind you that what we're looking for here is we're looking for the number of years. So what we're looking for is our T. And the only way that we can solve that is to use logs. So let's take a minute and solve this. Alrighty, so if we have to isolate our base, in this case, which is E. So the first thing we're going to do is, well, the first thing I want to do is I want to flip-flop these because this makes me nuts, you know that. So 500 E to the 0.035 T is equal to 600. And isolating that E means we have to divide both sides by 500. So you get E to the 0.035 T is equal to 6 over 5, which is approximately 1.2, which is 1.2. All right, so now the only way that we can solve for T in our exponent is to log both sides. So if I take the log of both sides, I get log E of 0.035 T is equal to the log, and just for ease of calculation, let's use 1.2. So using our power law, it's 0.035 T is equal to, log E, T log E is equal to log 1.2. Now we're solving for T, which means the first thing I'm going to have to do, and actually what you can do, you can only do it in one step if you want to, we have to divide by 0.035 log E. 0.035 log E. So let's put this into our calculator. We're going to spend some time tomorrow doing this, and I'll show it to you then, but this turns out to be 5.2 once we round it. I don't want to spend time showing you on a calculator that you do not have in front of you. All right, so write down what you need to. Try to make sense of that one more time, and we'll move on to exercise 3. Because of the importance of y equals e to the x, its inverse is known as a natural logarithm, and it's also very important. The natural logarithm, which is the inverse of y equals e to the x, is y equals ln of x. All right, instead of saying log, we say ln of x. Basically, what we do is we translate that. One more time, we can translate that to y equals log base e of x. All right, so the natural logarithm, like all logarithms, gives an exponent as its output. In fact, it gives the power that we must raise e to in order to get the input. And the same laws of exponents and logarithms apply to natural logarithms. All right, so we're going to use our law that we just came up with, and we're going to translate these. So the natural log of e is, so ln of e is equal to log base e of e. So what does that mean? That means e to what power gives me e? So the natural log of e has to be 1. We can do the same thing for this one. So this says the natural log of 1 is equal to log base e of 1. Now we translate that to e raised to the what power is equal to 1, and we know this has to be 0. So the ln of 1 equals 0. These are all very important numbers that you will need to know. Now, natural log of e to the 5 means we have ln of e to the 5 is equal to the natural log, the log base e of e to the 5. I'm kind of getting into my other problem here. So what does this mean? This means e to the what power is equal to e to the 5th. So here the ln e to the 5th is simply equal to 5. And our last problem, we're going to, of course, rewrite this as natural log of e to the 1/2. I'm sorry, I should put that inside the parenthesis. I don't want you to think we can use the power law there yet. E to the 1/2 is going to equal log base e to the 1/2. So what that's saying is e to the what power is going to equal e to the 1/2. So that means the natural log of e to the 1/2 is simply 1/2. So hopefully you're seeing how this works. It's very similar to logarithms. You're just using a different base. Write down what you need to before we take a look at exercise 4. So like I said, the 3 basic logarithm laws that apply to logs also applies to natural logs. So we can do the same expansion that we did before. So here we have the natural log of x cubed over e to the 2nd power. So which is equivalent to that? So let's rewrite this. So the way I need to separate this is by subtraction. So I'm going to have the ln natural log of x to the 3rd minus ln e to the 2nd. Use my power law now. So this is 3 ln x minus 2 ln e. And we just remember that the natural log of e is equal to 1. So this is 3 ln x, which we can't do anything, minus 1. Times that 2, don't forget about the 2. So you get 3 ln x minus 2. And here's our answer right here. All right. So moving on to exercise 5. This one is a little bit more complicated. A hot liquid is cooling in a room whose temperature is constant. Its temperature can be modeled by the exponential function, shown below, which is right here. The temperature T is in degrees Fahrenheit and is a function of the number of minutes M. It has been cooling. So A says, what was the initial temperature of the water at M equals 0? Do without using your calculator. Well, I'm going to remind you that the initial is going to be the number sitting in front of your base, but because we have a plus 67 here, you must make sure that you're adding that on as well. So you have to say, so it's going to be 101 plus 67, whoop, the board is writing like a spooky person, which is 168 degrees Fahrenheit. Always make sure you put your units in. How do you interpret the statement that T of 0 equals 83.7? So I'm going to remind you that this represents your minutes. So basically, you're going to write if in 60 minutes, I don't know why the board is writing like this, in 60 minutes, the temperature of the liquid is 83.7 degrees. So being able to interpret what the question is asking and what information is given is just as important as getting the problem correct. So let's slide this up a little bit. Using the natural logarithm, determine algebraically when the temperature of the liquid will reach 100. So again, what they're giving me is they're saying T of M is equal to 100. All right? So they're saying when the temperature, so we're looking for T. Show the steps in your solution and then make sure you round it to the nearest tenth of a minute. All right, so let's using our formula now. We know 100 is equal to 101 times E times 0.03 M plus 67. All right, now again, in order to solve this, you need to isolate that E. So the first thing we're going to do is we're going to, I'm going to flip it. That's the first thing I want to do. 101 e to negative 0.03 m plus 67 is equal to 100. I'm going to minus 67 from both sides. And we get 101 e to the negative 0.03 m is equal to 33. And then we need to divide both sides by 101. So you get e to the negative 0.03 m is equal to, and I'm going to leave it as 33 over 101 because it's not a nice number. All right, now we need to log both sides. So, but now we're going to use natural logs. All right, so we're going to use our natural logs because we're using base e. So the ln of e to the negative 0.03 m is equal to the log, oh, see, ln, maybe you do one side, you do the other side, and ln of 33 over 101. All right, and now use your power law. Now some of you might have been able to skip this step. M times the ln of E is equal to the ln of 33 over 101. At this point now we need to remember solving for M. This is what I need to isolate. So I'm going to divide by what's ever left. So there's negative 0.03 ln of E. Divide both sides by negative 0.03. Well, the ln of E we know is 1. So if we want to, we can actually even just get rid of that. Right? So get rid of that. And then put this whole thing right into your calculator. And you will come out with 37.3 minutes. We should put M equals. Again, we'll spend some time tomorrow practicing this in our calculator. All right? So if you need to rewind that and take a look at that, because that was kind of a long problem, feel free to, okay? Before we move on to the next one, letter B. Okay, moving back up to B. On average, how many degrees are lost per minute over the interval between 10 and 30? Ooh, this is a great question. Round to the nearest tenth of a degree. So what we're talking about here is the rate of change. So we're going to work on this the same way we worked on rate of change problems before. We know that one of our points is 10 comma something, and the other one of our points is 30 comma something. So in order to find the y value for the 10, we're going to say t of 10 is equal to 101 times e to the negative 0.03 times 10 plus 67. You put this whole thing into your calculator and you get 141.8. So that number, 141.8, goes up here. So then we're going to do t of 30, which is 101 e to the negative 0.03 to the 30 plus 67. Put the whole thing into your calculator and you get 108.1. And that goes here. Notice we are rounding it to the nearest tenth of a degree. All right, but now you actually have to find the rate of change. So the rate of change is going to be the change in y's, which is 108.1 minus 141.8, over the change in x's, which is 30 minus 10, which comes out to be negative 1.7 degrees Fahrenheit per minute. So you can see how it is decreasing at this point. So it's losing, because that negative, so there's another way to interpret this. You can say it's losing 1.7 degrees Fahrenheit for each minute that it's sitting. Okay, and again, I don't know if you're going to be able to do this on the calculator you might have at home, but we'll spend some time in class and we will make sure that you practice that and being able to use the e and the natural logs, which is located by the way right near our other log. If you look here, here's our log right here over our 10 to the x, and right next to it is our natural log. So it's right in the same area. All right, so we will pick up with this tomorrow or the next time we meet, and until then, make good choices. And if you need to rewind at any point to rewrite things, feel free to. My apologies, this was a long video, but I hope that you understand the concept here. All right, thanks so much. Bye-bye now.